welcome back to another exciting edition of Turdferg Vision, version 2.0, I guess. Obviously, where technology's improved a little bit. At least I hope so. But anyway, this video that we're going to be making, it's a classic representation of the old shoot the monkey problem. And in making this video, in no way do I advocate the shooting of monkeys, unless they're making that face or perhaps throwing poo at you somewhat. But anyway, usually this problem starts out, they've got a gun, there's a monkey up in a tree, and they're going to try and shoot the monkey out of the tree. So anyway, a lot of times, a lot of teachers do this. They do the demonstrations. They even want you to prove something mathematically, but they never really explain it. So what are they trying to get you to prove? And even as I'm looking at what I wrote, I'm like, wow, does this really make sense even to me? Prove that if the gun is aimed at the monkey, then the projectile will strike the monkey because the time to position function is, excuse me, that should definitely be an is right there, is the same for both the projectile and the falling monkey. So anyway, all we're going to do is we're going to try and put this together. That if you take a gun, and I hope this technology works for me here. If you were to take a gun and aim it, boom. So if you tried to aim at this monkey in the tree, see if we can, let's try that one more time. If we took the gun and aimed it at the monkey up into the tree, so here's my projectile, and of course, like any projectile, I'm going to have some kind of, I'm going to write VOP for velocity initial of the projectile. And of course, I'm going to be shooting it at some angle of theta. If I aim this gun at this monkey, I should be able to strike the monkey and shoot out of the tree. Well, here's the thing. The projectile is not going to just go shoo straight up and at the monkey. So what's actually going to happen in this problem is the projectile is going to make a parabolic shape. It's going to behave like a projectile. Once launched, and you already know, and this is not a video for like new learners. If you're watching this, you should already have a little bit of physics experience, and that's not really even a very good projectile, but it serves the purpose. So at this point, let's ignore this monkey up here and just look at this projectile, and it's doing what projectiles do. It goes up, 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 and then here it's coming down, 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 down. So when we're looking at this projectile, one of the things I'm going to be concerned with over here is this position that this projectile is off the ground. I'm going to call that position, I'm going to call that Y. So there is my position over here. And so here we've got, and again, you can ignore the monkey, but here you've got this basic projectile problem, which also means if this is a basic projectile problem, then that means we're also going to have to assume in this problem that we've got this velocity is made of two components, because again, we're just looking at this like a plain Jane projectile. That velocity is made of two components. Those two components being, you've got a VOPX and you've got a VOPY in this problem. So we've got VOPX and VOPY. And of course, velocity initial projectile. To find the x1 down here, to find that x1, I will go VOP cosine theta, and that'll give me my x. And now to find this y value up here, we'll come back VO. It's taking me a little while to get used to this. VOP. And that's how I can find it. So far, all we're doing is we're looking at a plain Jane, basic looking projectile. What makes this problem has got to do with the fact that you're going to hit that monkey. And again, I do no way advocate the shooting of monkeys. But let's do something. I want to try and take a look at something. This monkey, I'm going to say, is up in the air a distance of h. So here we've got this monkey. He's up in the air a distance of h. Now, the key to making this problem what it is boils down to this little fact. When this monkey, what happens is this: when you shoot your projectile, I guess you could say it scares the monkey and the monkey falls out of the tree. So, and which is the worst thing the monkey could do. The monkey just needs to stay hanging in the tree and he's completely safe from this projectile. But anyway, he gets scared, monkey lets go, and here comes the monkey falling to the ground. So the monkey over here, he gets scared, releases, and here comes Mr. Monkey falling to the ground, which is bad for the monkey for sure, because obviously at this point he's going to be hit by the projectile. So the whole point of this problem is trying to prove that the time function, time to position relationship, the time position, it's going to try and prove that this is the same for the monkey as it is the projectile. So as long as you aim, there's two things have to be in here. One, you have to aim, and I guess second, it has to be in range. If you are not in range, then it's pointless. If this monkey is somewhere way over to the side, then it doesn't matter. The projectile would hit the ground before it ever hit the monkey in the first place. But we got to have a couple of little minor league conditions there. And I'm going to tell you, the part where most people mess this up is, I'm going to show you, it's right here with the monkey part. See, the monkey is going to fall. The monkey falls. You have to get that. If I gave you this distance, you'd write like -5. The monkey falls 5 meters. Well, here's the thing. This is not, I don't have a number here. All I know about this is its relation to h and y. And that means that this function right here, we know this. We know that monkey is going to fall a distance of h minus y. That's what I know about Mr. Monkey. But listen to what I said. The monkey's going to fall a distance of h minus y. So when I go to write this in an equation, I'm going to write that down. I'm going to write it like that. He's going to fall h minus y is what I'm going to do. And so far, the biggest problem I've got with my little toy is it usually doesn't scroll. Hey, it did pretty good just then. So let's kind of split this up, and let's come over here and let's look just at the monkey over here. So let's take a look at just the monkey. Well, we just said a little while ago, you know, there's not a whole lot of equations that apply to this monkey. First equation, in terms of kinematics, that gives us a velocity. Second equation doesn't have time in it. And remember, we're trying to relate time and position. So if I'm trying to relate time and position, what's the only equation that's going to relate time and position? Well, that's going to be our second kinematic equation. That's going to be it. So our second kinematic equation, generically written, I'm going to write it as y equals VOT plus 1/2 AT square over here. So here's our monkey, VOT plus 1/2 AT square. Now, as I'm looking at this, I'm going to try and remember something. Remember, this is just my generic equation. That's just the generic. It doesn't mean a whole lot to me. I do know something, though. I know that VOT is going to be 0 because that monkey was just hanging at rest in this problem. I also know this. I know that my position is actually going to be negative h minus y. I know that as well. And so that's going to be equal to And I guess the only thing we've got left is just this 1/2 AT square. And that's the only thing we've got left in this problem. We can clean this up. Let's distribute that negative sign. That's pretty trashy looking over here. So let's rewrite that as y minus h equals 1/2 AT squared. And I've kind of done half of what I wanted to do. I said at the beginning of the problem, I want to write a time and position function for both the monkey and the projectile. And we have successfully done that. We have wrote a equation for the monkey. So the whole purpose of the teacher asking you this question, they want to see if you can write this same function for the projectile. So can we write this, can we derive this same function for the projectile? Well, let's find out. Obviously we can, or I wouldn't be making this video, and the little demonstration wouldn't work so good at this point. But anyway, so here we've got our projectile. Let's ignore Mr. Monkey and let's look at the projectile over here. Remember what we're trying to do. Time, position. What is the only equation, again, that has both time and position in it? Well, we can write the same generic equation. Y equals, I'm going to write something different though. This is a projectile. And so when you do projectiles generically, you should write something like this. It's 1/2 AT square. So there's my generic. Now some of your teachers might write minus 1/2 GT square here. Get real, big kid. That's not something you've got to be doing. As long as you know that we're going to use negative 9.8 for our acceleration in this problem. But anyway, if you've watched my other videos, you already know how I do this. But anyway, I'm going to do one little thing. I'm going to put a little P jammed in there since this is my projectile problem as we talked about up here. Well, let's go ahead and do something. Let's go ahead and substitute in place of VOPY. Let's substitute VOP sine theta. So let's rewrite this. And I don't have to change the y because I've used y already. So I'm going to rewrite this as y equals VOP sine theta t plus 1/2 AT square. So VOP sine theta t. All right, so that's looking pretty cool. But you can see at this point, this looks absolutely nothing like, boy, I gotta get used to writing on this touch screen. Anyway, this looks nothing like this. Now I've got the 1/2 AT square, and I've even got the y, but that VOP is horrible nasty. Well, let's start running through our head. What are some other projectile equations that we know? Wait a second. I know a very, very, very common projectile equation. Wait a second. X. Yeah, that's an X. So we've got Y, we've got X, and I know that X is equal to VO X T. And wait a second, I know that VOX is this VOP cosine. Wait a second, my X is, let's rewrite that. Maybe somewhere we've got a little bit more room. So let's write this X expression. X is equal to VOP cosine theta t, which means X over VOP cosine theta is equal to t. Hold on. I can take this and substitute it right here. Uh-oh. Now this is about to get interesting. What's going to happen now? Other than my writing probably gets worse. Y equals VOP sine theta. And in place of that t, I've got X over VOP cosine theta. Now this is interesting. Plus 1/2 AT squared. Well, I still don't have this equation. But wow, look at what's going on here though. I've got some neat stuff. What's going to happen to this VOP and this VOP? I got a VOP and a VOP. Wait a second. That means that the VOPs are actually going to cancel each other out. And I see one more thing that's neat. I've got sine over cosine. That means I can rewrite this as y equals sine over cosine is tangent x plus 1/2 AT squared. Now again, it's getting closer, but it's still not the same equation. So how can I get these the same? You know, the first time I ever did this problem, this is actually where I got hung, like back in college. So I got hung right here. So how do I put these two together? You know, it took me a second. And then I finally, you know, when I was staring at it back in the day, I was staring at it. And then all of a sudden, I kind of really picked up on something. See if I can get me a line going here. I want me a nice line. Bam, make that sucker big. I want a Buick of a line. I want to be some color I ain't even used yet. Yellow. Bam. I don't know if I can see yellow. We'll find out. I noticed something. Look at this shape. Do you notice what we've made here? I've got in this problem, I've got a right triangle. And that's actually the key to doing this whole problem is you recognizing that there is a right triangle in this problem. Let's look at that triangle. Boom. So I've got this great little right triangle. And why will it not, the stupid, oh, sorry, my thingy is still not, according to this, I'm supposed to be using a pen. Oh, wow, I can draw smiley faces now. All right, here we go. We're going to actually try and see if this pen works. All right, so there we go. That's X. This was that monkey up in the air. Theta. Wait a second. Wait a second. Tangent. Tangent theta is equal to the opposite, which is H, over X, the adjacent side, which means X tangent theta is the same as H. Wait a second. It's right there. It's staring me in the face. Y is equal to H plus 1/2 AT squared. Which means, move the H over, Y minus H is equal to 1/2 AT squared. So in other words, the equation for position as a function of time is the exact same for the projectile as the monkey. Whoa! That is the entire purpose of this problem, is this derivation of these two equations on here. Well, I guess this does it for me, so I'll say goodbye. Might take 1 second here and see if I can try out one of my cool new little pen items on here. So far, the problem I'm having is my computer is actually not good enough to actually be doing this software. But anyway, so for now, wow, this computer is terrible. I'm trying to write the really cool letters and it won't. It's so dumb. It can't do it. Oh well. Bye. Bye. From. Oh, there it goes. Third Ferg 67. Bam. Took me 20 minutes, but finally did it. All right. Bye. Thank y'all.